Okay, so thanks a lot, especially thanks to the organizers. It's for inviting me and giving me the opportunity to talk about what we do here in Pisa. And I must tell you, this is the most challenging conference I've ever been to in my life, because you bring I'm a sommelier in a spare time, and you bring a sommelier to a wine place, so it was a disaster. So yesterday was pretty tough. Okay, I hope I can make sense. Right, so today I'm going to talk about stuff that was done by, very nice, we're talking about students with Jenny, so very nice students at the University of Pisa. I moved back there from Manchester in January 1st, 2020. And, Gian Marcello Andorina was a PhD student of mine, is now Collège de France in Paris, and Riccardo Riolo is a current PhD student. This has nothing to do with qubits, so apologize. It's all quantum, but there are no qubits, okay? So the only qubits are in a startup that I raised during the pandemic, in fact. So the operation started in 2023 with a colleague of mine at Scuola Normale, which is a nearby university. Is a monster of quantum information theory. My colleague is Vittorio Giovannetti, and we are collaborating for fabrication with the VTT, and then Francesco. We have a collaboration with Francesco Giazzotto, which is also from Scuola Normale. We are doing hiring, so please, take a look at this website if you're interested. We do, we can talk in the coffee break. I can't say much here, but I would be happy to talk over lunch. Okay, so today I'm going to talk about stuff. So it's a big field, subfield, involving a lot of people, and I'm going to give you some names later of people you can refer to as pioneers really in the field. The idea is essentially to use vacuum fluctuations of a confined electromagnetic field to change the properties of matter. Okay, I will give you a few examples in a second. So these all, this physics at equilibrium has nothing to do with Floquet engineering. So we are not pumping the system because that produces heating typically. So we would like to do everything in a passive cavity without optical pumping. And that cavities can be used. That's the angle of attack. As you have heard earlier, qubits are probed by cavities. Through wave-guided modes and stuff like that in circuit QED. This is cavity QED, and you can use the cavity both to change the ground state, and this is a ground state of a quantum material, but also to probe phases of matter. Okay, so that's the outline of the talk. It's full of equations. I apologize. We were lucky to start the conference with an experimental colleague. And, these are quite a few papers that you see that are also experimental names by, a few people like Pablo Arillo Herrero, Claudia Felser, Frank Coppens. And one of the problems of this field is it's theory dominated. And, as you know, condensed matter is an experimental science. And there are very few experiments. I'm going to talk about one experiment only, and, our take on this experiment. So we really hope that a few people jump in and do lots of experiments on this. So we really like this. Okay. So let me tell you what's the point. So the point is the Holy Grail, sorry for a lot of text here. And as I said, lots of pioneers. I think this field was started by Thomas Ebbesen back in 2012. The idea was to do to change chemistry, in fact, right? So you put molecules in a chemistry. It's an entire field now called polaritonic chemistry, and you can change photochemistry in a cavity. So Ebbesen has had a lot of influence in this field, and certainly, we had a couple of days ago back in Pisa, Angel Rubio is, Max Planck, and then a Flatiron has had a lot of impact, and quite a few other names that you see here, and these are really authoritative reviews. I really suggest you to, if you want to, read what's going on, read these papers here. So as I said, so the idea is that, let me give you an example, right? You have a superconductor with critical temperature Tc outside the cavity. You place it in a cavity, and, cavity is an object, think about it as, two metallic mirrors, like a Fabry-Perot cavity. I'm going to talk about other cavities, which are polariton cavities. But essentially, and you change Tc. So this is the Holy Grail. That's how the field started. As you know, Andrea Cavalleri was, was doing a lot of experiments with, pumping materials, and then he's also very excited about doing these changing quantum fluctuations of matter by placing systems in cavities. So that's the holy grail, right? So can you change TC? Even if you do worse, right? Even if you lower it, it's conceptually interesting. So point number one, can you change the Curie temperature of a magnet, of a ferromagnet, an alter magnet, since we are in Mainz, or the Curie temperature of an antiferromagnet? So these are the type of questions, and believe me, they are very, very, very subtle questions. So, a simple take from a theory point of view could be, yes, you can do that. We have a lump shift, right? There are plenty of examples in theoretical undergrad physics in which the quantum fluctuations do something important, right? Casimir-Polder forces between bodies, they're small effects because speed of light appears there, so they tend to be small effects, but the lump shift is measurable, right? So for single atoms or even macroscopic bodies, quantum fluctuations, standing waves of the EM field have an impact, okay? So the question is well posed, and you can ask yourself, what about, instead of using single atoms and molecules, by placing, twisted bilayer graphene, for example, in a cavity or, an exotic correlated material. So these are the type of questions, okay? Okay, so, for the theory, I was expecting lots of students. I see a lot of young people, much younger than me, certainly, and, just for the theorist in the audience, I apologize for the, how trivial this slide is, but believe me, you have to obey certain principles, right? You have to work with the Hamiltonians that respect gauge invariance. Subtle, idiotic as it may sound, there are tons of paper in which you predict everything you want if you don't have gauge invariance and particle number conservation. So it's, believe me, it's interesting. So, point number two. Light-matter coupling tends to be weak. We know very well this. In vacuum, it's weak, as I said, because, alpha, that's why Feynman became famous, right? Because alpha, it's 1/137. So it's small effects, and you can't, at will, choose, to boost the light-matter coupling at will. So you have to be careful, and I'm going to raise a point about this. In fact, different cavities are expected to give very different types of physics. So there are what we call diffraction-limited cavities, just Fabry-Perot cavities, two metallic mirrors placed at distance d, quantum material in between. The simplest possible cavity, right, that you can think about. There are much more subtle cavities, which are called subwavelength cavities. In those cavities, essentially there is a polariton, which is an hybrid quasi-particle between light and matter modes. The most idiotic one is a plasmon polariton, right? We are talking about physics of 19, Gell-Mann-Bruckner, so Bohm-Pines, 1950. It's a plasmon polariton. You go in a beautiful cathedral, and that's why mirrors look so nice, because there are plasmon polaritons, right? Colors in mirrors, they're made by metallic nanoparticles like silver and gold. That's why they interact very strongly with the free space electromagnetic field. And so these cavities allow you to confine EM fields to very small spatial scale, much below the free space wavelength. So the free space wavelength here, it's the diffraction-limited wavelength lambda d, which is just, it depends on speed of light and frequency omega, but polaritonic cavities allow you to confine EM fields to very small length scales. And so so you can define a dimensionless number, which is called mode-volume confinement in this field, and that's essentially the ratio between the polariton wavelength you're working with, can be a plasmon polariton wavelength in a 2D material, like graphene, for example, in units of the free space wavelength of light. That's a dimensionless parameter, and this number tends to be very small. If you look at papers by Dmitry Bazov, Frank Coppens, the early days of polaritonic physics in 2D materials, this number can be humongously small. And so, 1/this number, it's a very large number, and people usually say, oh, good, I do the math in the simplest possible way, then I know that, I can tune interactions and make them very strong because I can use polaritons, right? And I can have this 1/A factor, which is a huge factor. But you have to be careful. That's a third warning. when and how to use this mode volume confinement to boost, to have an effective fine structure constant, light matter coupling, which is not 1/137, but it's boosted to very large values. I can skip this slide in the lack of time, but one of the points that I want to raise today is, okay, how do you couple matter modes with a polaritonic cavity? Okay, so that's and how you measure then in the lab quantum fluctuations of these electromagnetic field. Okay. Well, you don't have to invent anything. You open the right volume of Landau-Lifshitz in theoretical physics and you find it, right? You open, I know why people, didn't do this back in 2012 or so, 2014, but Landau-Lifshitz was already there. So you open Landau-Lifshitz and you open volume 8 of Landau-Lifshitz, and you find something which they don't call it like this, but it's a Green's function approach. We know that, in physics, Green's functions, for theoretical kids in the audience, they are very, very useful. And you just have to, there are Maxwell equations there, and you have to use and introduce Green's functions. Okay, so now I have 20 slides of math that I would like to simplify. So let me simplify to the core, especially for our experimental friends. So these are Maxwell equations. Okay, so the only assumption I'm going to make, is that fields in the matter, D and B, are linearly related to the microscopic fields E and H. That's the only assumption I'm going to make, which is linear response theory, and there is not a single polariton experiment in which you violate this linear approximation. It's also a local approximation. You see, the field at point R in space there is only one R. There is no non-locality in space. This is a local equation. That's an approximation. That's an approximation. Again, it works very well, but there are very interesting materials. Sugar, tartaric acid in wine. Louis Pasteur, second half of the 1800s, he discovered natural optical activity. So the fact that it's not Faraday's, so it's an effect that it's there in wine. And it's a very important effect. And twisted bilayer graphene, by the way, think about this. Ji Won Park discovered natural optical activity of twisted systems well before Pablo did the superconductivity experiment, okay? So there is plenty of chiral matter, not only sugar, but also, twisted materials, they are chiral. So, if you want to do a cavity with TBG, these local assumptions must be, you have to go beyond and open another chapter of Landau-Lifshitz. It's just going to another chapter, and so it's very easy to do technically. Okay. Long story short, you do all the algebra and you discover what's very, very clear. You discover that a cavity in general, or a confined electromagnetic field, can do two things. The scalar part, phi, and you get the electric field out of it, as you know from high school, minus the gradient of phi, is the electrical component of the confined electromagnetic field, obeys the Poisson equation. So in free space, we know the solution of this equation. We know that there is a Coulomb force and two electrons interacting with, with long-range Coulomb interactions. They have an interaction law which is 1 over distance. That's it, 10 minutes. Very good, yeah. And okay, so what the cavity does, it's through the environment and the polaritonic environment, it can dramatically change the electron-electron interaction. That's point number one, okay? So subwavelength cavities, that's what they do. They dramatically change electron-electron interactions. Point number two, there is a transverse component, which is the one that you read in the Lifshitz theory of Casimir-Polder effects. And that's essentially small. That's the one which is small in a subwavelength cavity, because it's a relativistic effect which has the speed of light everywhere. So VF, speed of fermions divided by speed of light, it's a small parameter typically, right? VF over C in graphene, for example, it's 1 over 300. So the effects are pretty small when you go to this transverse field. So the main effect of a cavity, bottom line, if I run out of time, is that you can tailor the electron-electron interactions which acquire retardation. They become also frequency dependent. When I tell you this, any theorist in the audience should stand up and say, wow, then you can make superconductivity. Yes, Okay, so I don't have time to discuss that, but you have polaritonic mediated superconductivity that, and we are actually doing calculation. But you can do something easier. So let me go to the core now of the talk. You can change and alter DC transport, which sounds paradoxical, right? Because you're talking about finite omega, but DC transport is DC transport by definition is an omega equals 0 property, right? So is there any contradiction? So there's this beautiful experiment done at ETH by Jérôme Feist, and there are other experiments at ETH. It's pretty much the only experiments. These are split ring resonators. They are small metallic objects, relatively small metallic objects, coupled to an ordinary two-dimensional electron gas. Parabolic band is gallium arsenide. And Jérôme noticed that you can actually change the amplitude of the Shubnikov-de-Haas oscillations. So that's an omega equals 0 property. This technically, Shubnikov-de-Haas, I remind you, I'm plotting here longitudinal resistivity as a function of an applied magnetic field well before quantum Hall effect shows up, okay? So how come a cavity can modify this? If a cavity has finite frequency polaritons, how can it modify DC transport? There's been some theory by Cristiano, but we disagree with the theory that was published with Cristiano, and that's our take on this. The idea is extremely simple. You open other classics. I don't want to make the joke again and again, but okay. So it's Lifshitz theory and Lifshitz-Koszewicz theory of Shubnikov-de-Haas oscillations says something extremely simple. When you sweep the Fermi level through a ladder of Landau levels, you have high density of states, small density of states, high density of states, small density of states, and so you have these oscillatory phenomena like the Haas-Van Alphen physics. And so you have an oscillatory part here which is controlled by magnetic field, but the amplitude of the Shubnikov-de-Haas oscillations is completely controlled by the so-called cyclotron mass, which is essentially for a parabolic band to DEG, I'm saying this for people like Alex and so on and so forth, is a Fermi liquid parameter, is how the band mass of the electrons is changing. For massless Dirac fermions, like in the case of graphene, essentially is the fact that you have a Fermi velocity here, which is not the bare Fermi velocity. So as everybody knows in the audience, this was a big thing a few years ago in graphene, okay? So all I am saying is that what the cavity does, since it modifies the electron-electron interactions, modifies exactly the cyclotron mass, which is a Landau Fermi liquid parameter. That's why in the title of my talk I had the Landau theory of normal Fermi liquids. So that's what the cavity does and changes the amplitude of the Shubnikov-de-Haas oscillations. But since I'm running out of time, let me tell you something very important. Okay, so you have a renormalized Coulomb interaction, which is not 1/r distance and is frequency dependent. Be careful. There may be trivial effect for our experimental friends. Let me stress this. If you put a metal, a cavity has metallic mirrors, right? In the simplest example I was mentioning, and in general you have a metallic mirror to confine fields. That's a metal. It does image charges, so it screens the electron-electron interaction, giving you even an omega equals 0 trivial effect, which is just it's just screening, right, of electron-electron interaction. So placing a gate very close to an electron system can in principle change dramatically the electron-electron interactions, but has nothing to do with the fluctuations, the quantum nature of the polaritonic field. So you have to be a little careful. And so, we did a few calculations, and then I conclude just showing you some data for a 2D material embedded in a polaritonic cavity, where essentially these medium here, so there's a top metal gate, back metal gate, and our experimental friends in the audience will laugh. This is routinely done in the lab for 2D materials. It's a van der Waals structure with top and bottom gates, and the dielectric in between can be HBN, for example. In that case, there are very nice measurements about phonon polaritons back in 2014. It was the first natural material displaying hyperbolic phonon polaritons. This can be any medium you want. Can be STO, with modes in the terahertz. Okay, I'm going to show you some algebra. I'm going to show you some results. So let me skip this, but the physics of this is very simple. Let me explain the physics and then show you the results. Why Shubnikov-de-Haas oscillations change, not in frequency, but in amplitude. The reason is very easy. The white line represents the collective mode of the 2D electron system in the absence of polaritons. This is a plasmon, it's just a plasmon, a simple plasmon, maybe modified by the presence of a metal gate, so you don't see the usual square root of Q behavior, but you see an acoustic plasmon there because of metal gates. But these are the free carriers in graphene, essentially, screened by the metal gate. But now you switch on fine at omega. What happens is that this center of mass mode of the electron system couples to the nearby polaritons, because of long-range interactions is coupling between plasmon and the phonon polaritons in the polaritonic medium, and therefore spectral weight is transferred from the matter degrees of freedom to the nearby cavity modes. And so that's the physics of why you really change the amplitude of the Shubnikov-de-Haas oscillations. So you can do a theory of these. Let me show you some results. HBN not so good, as you already understood, because polariton modes in HBN are in the mid-IR, hundreds of MeV. So typical spectral weight is concentrated for an electron gas in the terahertz. That's where the plasmon carries a lot of spectral weight, which is typically in the terahertz. And HBN not so good as a polaritonic medium to see a vacuum QED effect, because polariton modes are in hundreds of MeV. So you have to find something else, and I'm not an experimentalist, unfortunately, and or fortunately. And you know, and so you see that there are other materials out there, and you know, these are, for example, topological insulator thin films. They have polariton modes down in the terahertz. STO, if you look at it, has even phonon modes which are very soft, as you know, because it's proximal to an instability, to a ferroelectric instability, although it remains quantum paraelectric down to very low temperatures. So you gotta find some nice material, marries well with graphene, and that's why HBN is the favorite of our, from our experimental colleagues. Maybe it is not so good because it would decrease a lot graphene quality. It's a matter of, electronic quality, and I don't know, so this is incorporated, in fact, in the theory. At least phonon losses in the medium are incorporated. But for example, there can be a surface layer here, right? There is a mode at the surface in a topological insulator thin film, and maybe that can couple to the electron system too. So you have to be careful and do some fine tuning. Let me give you some numbers, and then I conclude. So you see, let me give you the example here with this proper terahertz material in which there are polaritons at very low energy. This is a plot of how the Fermi velocity changes with gate voltage, so as a function of electron density. So free space would be the dashed line. In the presence of the cavity, you have a large suppression of the Fermi velocity. Well, we know because there is large screening from a topological insulator thin film, because it has a small band gap, and so that screens well. But if you do the math well and you plot what's the QED effect, as a QED effect which easily reaches 7 or 10%. It's not a huge effect, but it's much, much larger than you would have in vacuum with graphene interacting with free space EM fields. And this is now a matter of material science, finding partners for graphene which are polaritonic media, as I said, with modes down at very low frequencies. So let me conclude now, because I think I'm running out of time. And then, I'm very happy to talk about all the details you wish over the lunch break. So, especially for the theorists, number one, there is no fudge factor. You don't have to invent anything. You open, the classic books, and I give you a cavity, and you calculate the Green's function of a cavity. Okay. So if you like COMSOL or your EM solver, use your EM solver. In translational invariant systems like the cavities I was showing you. You can do Green's function calculations analytically, but any cavity you give me, we can calculate the Green's function for you and couple it with the electron system and make quantitative predictions. Subwavelength cavities are dominated by this electric field-like component of the M field, And essentially what it does is that, it changes electron-electron interactions and introduces, in fact, retardation. So our hope, and there are now, so we have a code now, we are benchmarking the code, and the hope is that you can induce superconductivity by finding these appropriate partners for graphene or other 2D materials. Of course, the next endeavor will be to put TBG and other twisted materials inside cavities, just not because everybody's doing that, but because there is a reason we can talk about it a little bit during the break. And finally, there's a nice physics point, and which I would like to raise. And so, as you know, the microscopic quantum Hall effect has been debated for a long time. And in gallium arsenide, there was very powerful tools to do, of course, transport, but also optical measurements of, fragile quantum Hall states and, fractional quantum Hall states by Aaron Pinchuk and so work back in the late 90s. Graphene has no band gap, right? So 2D materials, in particular the ones, semi-metals, they don't have a band gap. So you cannot use inelastic light scattering. So you can couple to finite Q collective modes of your electron system by making arrays of cavity. And that's what Frank is working on right now, because an array of cavity gives you a periodicity. A periodicity means a finite length scale, which in momentum space becomes a finite Q. So you can perhaps probe very complicated exotic modes of quantum materials by using cavities these times not to alter only the quantum material, but also as a system to probe fragile quantum Hall states in a non-invasive way. Okay, so that's the idea. So thank you, and sorry for taking longer. Yeah, thank you.